Okay, so welcome to the actual last lecture. I didn't realize that we had concurrency to go over as well, which is a fun subject. So apologies for the misdirection in the end of the last lecture. Also, at the end of this lecture, we're going to go over memory allocation, which was a subject that was sort of optional in this course throughout. I don't think it's going to be in any of the materials or the tests or anything like that, but we'll go through it because it's something that you may come across a fair bit, and you know we could have covered it a few weeks ago, but it sort of slipped through the cracks, and so want to make sure that we get a chance to sort of dive into memory allocation and what that looks like fundamentally, and how that works, because we've been talking a lot about dealing with the memory and the cache and all this stuff, but obviously you know uh, just taking malloc for granted is not always a good option. So it'd be good to understand how those things work and the downsides, the upsides, and how do we kind of improve those systems as well in terms of a real-time performance system. But for the meat and potatoes of this course, we'll be this lecture. We'll talk a lot about concurrency, and so first off, let's kind of discuss what concurrency is. So why do we even care about concurrency? Well, if you can imagine a computing system, most of these systems actually need to do more than one thing at a time, right? So think about your computer right now. You have maybe a browser open. Perhaps you've got a bunch of background processes that are, dealing with your keyboard and your mouse. Maybe you have a game running, which in of itself is doing many things concurrently, right? And so this is a more realistic system. If we had a computer that could only do one thing at a time, then we would have to sort of load our program, run the program, and then get the output, and then run another program. And back in the day, like, this is how computers did work. With like punch cards or whatever, you would set up your program, you'd run it, and you'd see the outcome. So the name computer, essentially comes out of that sort of definition of what a computer does, which is computes and goes through a bunch of different calculations and operations. But in the modern manifestation of a computer, we have many different things going on simultaneously. We don't necessarily want to always run and stop our programs. And obviously, we have to deal with other scenarios where we have multiple CPUs and many different resources. But at the core of it, a computer has a CPU, and theoretically, a CPU can only really do one thing at a time. As we saw, the CPU reads in an instruction from the instruction memory, loads that up, loads up the registers, and is really doing one thing at a time. Now keep in mind we have superscalar, so it's kind of doing multiple one things at a time, meaning it's doing multiple tasks, but essentially it's still running off of the same task. It's the same code. It's only running one program at a time. As far as the CPU knows, it can only do so many things. And I will talk about this a bit more, but later in the course. But another thing you would kind of want to think about is hyperthreading, and I'll come back to this after we actually discuss what threads are. But essentially, some CPUs are able to do multiple things at a time by sort of it's a layer on top of superscalar in a way where you can sort of fill in resource gaps with alternative tasks. So we have CPUs that can do one thing at a time and maybe sometimes two things at a time. But as I mentioned, we have potentially thousands of different processes running simultaneously on our computer at any given moment. And so how do we do that? Well, concurrency allows us to essentially treat the CPU as a resource. So instead of saying, okay, here's this CPU and it's doing one thing at a time, we say, here's CPU, and we can chop up the CPU into sort of ratios of time spent on particular tasks. And we can accomplish this in two different kinds of ways, which are very similar at the core, but at the same time a little bit different in sort of function. The main one is processes, right? So when you load up one executable and another executable, those are two different processes running theoretically at the same time on your computer. And then there's also what's called threads. And threads and processes are very similar from the standpoint of an operating system, but a thread is sort of part of a process. So a process may also want to do multiple things at a time, versus without having to spawn off different processes. It's a bit of a subtle difference, but in practice, a very, very important one. And so let's talk a little bit about the anatomy of a process. And so in any given operating system, you generally have what's called a process control block. And this is how the operating system manages and schedules processes. In Linux, this is actually done by the way of a structure called the task struct, which you can check out the link, and that's actually the code and the line of that specific thing. And you can see just how complicated this can get in practice. And so while a process control block doesn't have a very specific definition, each operating system and each system in general may have a different set of things that it's keeping track of. We can go through kind of the core things that a process needs to keep track of so that when a CPU, say, stops working on one thing and starts working on another, when it comes back to that thing that it stopped, it can start off from where it left off. And so the first thing that's pretty obvious is you need to have a counter, a program counter. And this program counter essentially counts into the instruction code of the process. And so the code of this process exists in memory somewhere, and this is actually a little piece of memory that the operating system manages that tells you, okay, this process is at this point in its memory. And then you also have to maintain the states of the CPU registers. And this is actually one of the most time-consuming aspects of multitasking, because every time we start a new process, we have to save the thing that we're stopping. We have to save that state, so all the different registers, all the different state of the CPU. Very often, by the way, this is done. This is a hardware-assisted mechanism, so it's not like the operating system has to know everything about the CPU. But the CPU also in of itself has to handle what's called interrupts, which we'll talk about later. And so even though this seems like a very hard thing to do, a CPU has to sort of do this regardless. And so it's not that hard to do, it just takes time because the hardware does it for you, but it's not this very quick operation. Another thing you need to do is maintain a pointer to the stack. And the stack of a particular process may differ from the stack of a different process. And just like a function stack would have, right? When you load up a function stack, you have a different stack, and you're doing that. And so the stack of a particular process is going to be a very particular section in memory. So we have to make sure that we're using the correct stack. This also kind of brings up a different thing that I haven't really talked about or mentioned in this slide, which is virtual memory. So a process block may be dealing with a different virtual memory lookup than a different process. And so keep in mind that all of these different things, also the operating system is managing which virtual memory blocks are being loaded in and how that maps to physical memory. And so hopefully the process control block either does that on physical memory, so it already kind of does that translation, or there's an additional layer on top of this. But assuming in this world that we don't have a virtual memory at all, we just have a cache and physical memory, this would be the kind of more simple thing. We have a process ID, so this is an ID that's just a number that essentially identifies our process in the context of the operating system. We have the running state, and we'll talk about the different states that are available to a process in just a moment, but you can imagine if it's running or not running or idle or something. We also have scheduling state and information, and this is sort of gets into how the operating system determines what runs and when it runs, and kind of managing sort of internal state of the process to determine those things, such as priorities. For example, if you have a visual driver, something that's updating your screen, you maybe want to run that much faster than a keyboard input, because the keyboard doesn't get input that often, whereas a screen has to update 60, 120, whatever frames per second. And so the scheduling state would be a part of determining that, hey, this process needs to be read or be hit this amount of times per second, otherwise we're going to have a problem, versus the keyboard is a lower priority. And we'll talk about some of the scheduling, how the operating system kind of determines what to schedule and what not to schedule in that way. Sometimes processes can spawn off new children, so I can have a process that opens up another process, and the processes are related, so that if I close the parent process, I want all the other ones to close as well. Sometimes there are other processes that are related but not children, so they're related but they're associated but not so. Sometimes the operating system will keep track of all of those things. And then we also have the memory management information, as I mentioned, right? Like how does this map into virtual versus physical memory, and so on. It also may have a limit, so we can say, okay, each process has a maximum amount of memory it's allowed to have, and also sort of how that segments out into the cache or into the physical memory. And then finally, and this is again another kind of sort of very operating system dependent thing, you may have different devices allocated to this process. So say the process is getting information from a particular driver, or is running through a memory access thing, or a peripheral access thing. Sometimes this also involves the file pointers and things like that. So this process is currently connected to a particular file on disk, and so sometimes the operating system would like to keep track of that, so that when a process closes, you can sort of close that file in the operating system as well. But this is kind of gets into the weeds of like operating system design and things like that. And if that's interesting to you, I would definitely recommend going deeper into that subject. It's it's a lot of fun designing these systems, and or at least understanding them, because at the core they're actually quite simple. So all the things that you were like, oh, how does a computer do that? Well, like it does. It's very much kind of written into code and into the struct, into the architecture of this operating system. And so yeah, this is sort of a general view of how a process gets maintained. And in different operating systems, you have a lot of different sort of parameters that go into, how to change this structure for the benefit of that particular operating system. Yeah. So, great. Once again, process can be in 5 different states. A process can be just new, which is essentially you've just created the process. That it's essentially just a struct sitting in the operating system. It hasn't been added to a queue. It hasn't been run. It's just kind of hanging out. And then an operating system will then create that struct and then add it to the running queue, and so it's ready. It's ready to be run. Perhaps it might not be running, so it's in the queue. But every time that the operating system says, "Hey, do you want to run?" It's like, "Well, I'm ready, but I'm not running yet. Something actually has to execute it." And so then there's a third state, running. So something is executed, it's running. And this also means, by the way, that it's actually being run. So when you're in a ready state and you say ready, let's go, it's not executing yet. It will get pushed into the running queue, but it may not be running yet, because only one thing can be running. Again, remember, multitasking is sort of an illusion. Our CPU is only doing one thing at a time. I'll talk a little bit about multi-core at the end and all that stuff, but assuming that we have only one CPU in our system. And so it's in the queue, it's ready to go, and then it's running when it actually gets kind of popped up. And then for some reason it stops running, it's waiting. And that's because if you're in a multitasking system and you're the only process running and you don't let anything else run, it's not really a multitasking system. We've just now kind of gotten rid of the need to queue up everything to run and stop and run and stop. But in a way, we're kind of in that same place. Because how do you run and stop? It just means that we've queued up a bunch of stuff, and then it's all going to run through one at a time. So if we really want to do true multitasking, we need to have a way for the process to sort of stop running, not end, but stop and wait for the next things to run, and then get to go the next turn. So there's this 4 state of waiting. And so you can kind of imagine these 2 states of running, of ready, now running, waiting, and then waiting and running and waiting and running, until eventually the process dies for a variety of different reasons, such as it ends, and so it kills itself, or something else kills it anyways, and then it's in dead. So it's a dead process, and eventually gets cleaned up as well. So effectively, to kind of go into depth, processes are created by the OS when we execute the programs. Programs can also create new processes, so you can do this with children. Also keep in mind that processes have priorities, so we have ways to kind of manipulate how often and how, in what way processes can run, and we'll talk a little bit about schedulers and how that works. And also programs can kill other processes. So, in fact, this is exactly how most processes get killed. Most programs that you run on your computer don't close of their own accord, right? They'll run forever if you let them, and then when you go and you actually click the X or whatever to close that process, what happens really is the operating system is saying, oh, the user wants to kill this program, let me look up that program ID, tell the program to kill itself, and the program then kills itself. And if it doesn't in a timely fashion, it will lock up your system, or the operating system will force it to be removed. And so, yeah, these are kind of the 5 different stages that a process can be in. Oops. So as I mentioned already many times, right, we have this sort of problem where a process is running and it needs to let other processes run. And if you have a system of many different processes and they're just sort of queued up sequentially, then we and those, by the way, may have also many threads. So if we have just a sequential system, we have to wait until every single process is done. So we do have to have a way to interrupt things. Otherwise, we're just waiting for each process to be done. And this won't work in particular for any kind of event-driven application and for games, right? Imagine if loading a file, like every time that you did anything in a game, that had to complete before you could do the next thing. And maybe that's okay for turn-based games, but for real-time games, when you hit the key, it would have to wait until it was finishing an animation before it registered that. And I'm sure we've all actually had that experience, right? When you're playing a game with high latency, what's happening is that the input to your keyboard is not being serviced quickly enough because other things are taking up the CPU. And so you can kind of understand the importance of having a really smart scheduler that then allows and sort of serves the different needs of the different systems in the computer at the relevant frequency and effectively speed, because otherwise you have latency. So say if I hit a key on the keyboard, even though it doesn't happen very frequently, right? I'm able to type only so fast as compared to, say, like a file loader. But if I'm loading a file from disk and it's like a 50 megabyte file, it's going to take a few seconds, and then I'm typing, I want my keystrokes not to have to wait a few seconds for me to see them show up, right? And so there has to be some kind of way to schedule certain things faster than others and so on. And so, yeah, what we're trying to do here is we're treating, again, the CPU as a resource, and that resource can be split up, but there's also a little bit more intelligence on top of that, of how do you split it up and how do you kind of deal with really important things that are happening, when they happen. There's a couple of different paradigms of schedulers. One is what's called a cooperative paradigm. It's a pretty rare one. We'll talk about both. And then also preemptive. And preemptive is just kind of a way to say that it preempts or interrupts whatever is running. So a cooperative scheduler is essentially where the OS does not interrupt the currently running process. So that means that every one of our programs needs to essentially know that it can run for so long and then it has to go to sleep and wait. So the program itself, the process itself, puts itself into a sleep mode. So essentially, we're assuming that processes will voluntarily yield the CPU, and to ensure that other processes can also gain resource access. However, if you'll have just one program that doesn't behave this way, or one program that has a bug, say that puts you into an infinite loop or something, this will lock out the entire machine or the entire CPU. And so this is actually the way a lot of non-OS level systems handle scheduling. So if you have like a one-thread event loop, this was true for a long time with JavaScript and Python and a lot of things like that, although the new versions have really kind of improved on that. This is also the way a lot of embedded systems do multitasking. So when you have a really small CPU and very limited things and you want to do a real-time thing, you can essentially design each process to take a certain amount of time, and so you just kind of add them sequentially. So you can see there are benefits to cooperative scheduling because it allows us to kind of create a pretty robust sort of sequence of tasks that you do this, do this, do this, do this, and they all kind of work together. But that means that you're generally building the entire system and not just individual components of that system, because otherwise, if other people have the need to build those components, then you don't necessarily know what those things will do and how they will impact the performance of your system. And so you don't see this generally in like operating systems that allow people to have third-party software. Although early operating systems did use this approach because preemptive scheduling does have a performance cost. And so when that was very critical, this was actually the way to go. I believe, for example, iOS, right? Like the first iPhone came out without multitasking, so you couldn't run multiple things. It wasn't until iOS 4 that you actually were able to support multitasking. And the reason was there technically was multitasking in the system, but not to a user. The user was only able to do one thing at a time. And that was very important to ensure that this very limited piece of hardware was able to do all the things that the user expected it to. Right, and so in cooperative scheduling, one of the classic problems is how do you deal with I/O? You have to make sure that I/O gets serviced because you can't interrupt anything. And so when I hit a key, we have to make sure that whatever is picking up that key is going to happen often enough, or each process does whatever. So there's a lot of problems here. With preemptive scheduling, the idea is that the operating system or a task will just be interrupted without requiring its cooperation. So this is a little bit more convenient in a way where I'm saying, okay, hey task, go do your thing, and I'm going to interrupt you whenever I need to. There's downsides to this too, right? Because the task doesn't necessarily know if it's going to get everything that it wants to do done. But that's up to the operating system to ensure that tasks get sufficiently scheduled for them to get the time that they need to do what they need to do. So essentially, preemptive scheduling kind of comes down to the two options of the two things of let the current task continue running until. Sorry, there's a typo in my slides here. But we let the task run, and then we interrupt it, and then we let another task run. And the policy that the preemptive scheduler uses is essentially determines what we do at any given stage. So do we interrupt? Do we let it keep going? Do we stop it and then let something else go? When we interrupt the task, what actually does this is what's called an interrupt. And an interrupt is a piece of software. And we'll get into interrupts in a little bit in the lecture, but this is really important because if you think about it, it's a piece of software that's actually interrupting other pieces of software. Like code is interrupting other code to then let other code run. But who interrupts the interrupt? Like what if the interrupt crashes, right? So this is a very critical operation. This context switch, while done by the operating system, has to be extremely fast and extremely reliable, because if there's a bug in your interrupt routine, guess what? Nothing gets to run, and so that's a really big problem. So talking a little bit more at the hardware level of what an interrupt is. An interrupt is actually code that runs as a result of a certain event, and this is usually a hardware level event. So an example of this is a timer or what's called a GPIO, or general purpose input-output state change. So say you have a pin into your CPU, right? CPUs have inputs and outputs. Say that changes from 0 to 1, and then that will trigger an interrupt. Or say you have a memory transfer state change, which is also, by the way, done by way of a GPIO input state change. Pretty much all interrupts that are not not internal to the CPU are done by way of GPIO state changes. With that said, there's a lot of internal states that can change, and that's usually what causes an interrupt. So it's a state change. And a timer is usually a hardware level thing where you can say, okay, I want this timer to go off every millisecond or every 10 nanoseconds or whatever. And that will call a piece of code. And that code is in memory. It's actually memory mapped. So the operating system, when you boot up a CPU, you actually tell it to put code into the interrupt service routines. There's a way to boot up a processor, and this is getting into kind of depth about how embedded works, but you can set these up before you load. So you can just say, okay, hey, and you just set the registers of the CPU that point to the correct memory location to then run that code. And again, all this stuff is actually done in specialized CPU registers. A lot of this stuff is hardware level stuff. And so you can disable or enable timers and other capabilities of the CPU by way of specialized registers. And so what you do is you set the value of these registers. And what's really interesting about this is the registers are not always actually registers. Sometimes they're memory mapped, so it's just a particular piece of memory that it dedicates to that particular thing. but many times it is just a register. It's just a state. So a CPU, while you have many registers that you're using for your operation of your program, it also has many thousands sometimes of registers that captures the state of the machine and like how the CPU is going to be running. So it's actually a pretty complicated or set of things, and it's up to you to manipulate that as an operating system developer. But as a developer of code running on an operating system, you never really have to worry about that. So a really, really important thing about interrupts is that, what I mentioned before, an interrupt is what's called when an interrupt fires, it launches what's called an interrupt service routine. And this is just code that runs somewhere. And if another interrupt fires during that time, you're not guaranteed to have that ISR associated with a new interrupt to be hit. So your interrupt service routines have to be very fast and very efficient, because during that time, other interrupts will be ignored. And there are a lot of mechanisms to kind of avoid this, and you can kind of queue them and whatever. So it's not so black and white, but keep that in mind. Your interrupt service routine is a very, very specialized piece of code that essentially tells the operating system, hey, what to do. And so you have to really be careful with those, because that's like the lowest level of code in your system. And it happens all the time. It's happening more often than you might imagine, because it's these timers going off all the time that are keeping your system chugging and ensuring that the correct piece of code is being run on the CPU at any given moment. And I think this is something that these days gets really taken for granted. But back in the day, right, like a CPU couldn't even be preempted because it was too slow, right? There are when I started coding, it was on 50 megahertz processors that were not superscalar and barely did any of this stuff. And so you have to be very, very cognizant of even interrupt service routines on these systems that barely could run Windows, right? So this is a very interesting subject, and maybe not one that gets much love, but if you're in embedded land, if you're working on little, very small resource constrained systems, this actually becomes a pretty big portion of what you're thinking about. So interrupts aside, now we know how processes get interrupted. How do we know what to run? So now we have a system that can run a task at any given moment, and it can interrupt that task and put it into a queue or into a set of processes. So how does it choose which one to go next? So there's a number of different scheduling policies, and I'm not going to go through all of them, but we'll talk a little bit about some of the examples here. And one of the most obvious ones is the first come, first serve, so FIFO. So in this case, you really have a queue. And the queue, basically, okay, cool, you're running. When you get interrupted, you get put back at the back of the queue, and the next task goes. So in this case, we basically just run it in the order that we received it. This is actually pretty effective when you know that your tasks are all about take about the same amount of time. And if all your tasks take about the same amount of time, then you can ensure that they all get seen and used in a given amount of time. You don't have the concern of what's called starvation or deadlock, which we'll talk about more in this lecture as well. So FIFO is actually not, it doesn't get much love because it's very boring. And you do have actually the bad situation. If that's not true, if the assumption is that an individual process may take longer than the others, then this is a really bad system. And in fact, as a single process is unpredictable, meaning it could take forever, you don't know, or maybe it has a bug or a problem, then this will cause essentially deadlock of the system. So that does have a problem where this may put the system into in a state that cannot be recovered. If you're only running them at a particular, well, that's actually not true. It won't cause deadlock because you'll run it and it'll go back to the beginning. But it does have the situation where a particular task will get starved out because it's not getting enough time, not enough time. So sorry, it won't cause a deadlock, but it will cause starvation of a particular task that needs more attention than the other ones. This also has the issue of real time. So if you have the FIFO and it's a very deep queue and one of those tasks is taking your keyboard input, that's a problem too, because by the time that it gets to the front of the line, it might have been too long. So you have to kind of keep that in mind in terms of how quickly, and as the queue gets deeper and deeper, if you're playing this game of, okay, we're gonna make sure that everything gets some percentage of the CPU time in a given frequency, right? The amount of time you give to an individual task goes down, or if you keep that amount of time constant, the amount of time before any given task is seen goes up. So you can see there's a lot of different kind of elements in regards to FIFO that you have to think about. So we can also talk about priority scheduling, and this sort of like always confuses me between priority scheduling and earliest deadline first to multi-level queue, because the multi-level queue is sort of a version of the FIFO but with priority levels attached. But earliest deadline first tries to predict which task is going to finish the soonest, and that's the one that not finish the soonest, because that's actually shortest remaining time. There's like a very subtle difference, but essentially which task has to be done the soonest. So this is very much for real-time systems. So say we have a keyboard service routine, or a keyboard handler, and we know we need to handle it within the deadline is when a user pressed a key, right? So we can somehow manipulate the input, the deadline, by hitting the key, and then it tells you. And so then we can say, oh, well, this particular task, so when we interrupt the current task and we look at the other tasks, we can see which task is the most late, is the most behind schedule, or needs to be due in the soonest amount of time. And that's the one that we run first. So this is actually a very difficult scheduler to write, because you kind of have to figure out and predict what task it needs to be seen soonest. But it's actually one of the most efficient. If you can actually get this, I won't go into depth, but I remember reading a lot about this recently, that you can ensure a lack of starvation, lack of deadlock, and the kind of the best latency here, because what will happen is the thing, it's almost like an ER in a way, right? When you come in with a broken arm and somebody else is coming in with like a heart attack, like the heart attack person preempts you, right? You have to wait a little bit longer because you're not going to die, but they might. And so this is sort of the ER type of scenario. And that's, I think, one of the more effective ways, because the things that need to be seen, need to get attention, get it when they need it. So this is popular for real-time systems. So the shortest remaining time first is a bit of a difference from this. It's not how late are we and how much attention do we need. It's more like how much time do we have left. So say you have four loops of 1,000, the one that has the least amount of time left to go would win. And that's the way that you would do it. And this sort of works pretty well for, not necessarily for real time. And it's pretty easy to game it, right? Because you could sort of say that you have a little bit of time left, but you don't, and you actually have a lot. It's very actually hard to develop this in a way, because a system has to kind of predict how much time is left in a particular process. And so, but in this case, it works quite well, and it is a relatively good and efficient system to schedule all of the tasks that need to get done in a given amount of time reasonably. But it doesn't work particularly well for like event-driven applications or things that will never end, because if that's the case, then things that are going to take a very short amount of time will always preempt you. And so then how do you choose between, say, a video game that's never going to end by comparison to a little application that's downloading a file? And so that's this one I haven't seen very much of personally, but is an interesting one to kind of talk about. Round robin is sort of it's very similar to the FIFO, but it's a little bit more, just like each person gets a certain amount of time, and that's it. Let me actually pause here for a second and get a little bit more depth on that. Okay, I'm sorry. So when I mentioned FIFO, that was actually round robin. So that's why I was kind of getting a little bit confused about there for a second. So round robin is essentially what I was describing before as FIFO, where each task gets a certain amount of time, and you kind of go through, and they go back and forth. However, the only difference with FIFO is not when a thing gets off the queue, it runs to completion. So that's a big difference than what I was describing before. It doesn't get put back at the beginning of the queue. That's actually round robin. And in round robin, everybody gets a chance to play. Every task gets a slice of time. And in FIFO, you actually have to go one at a time, and you just sequentially schedule everything. And this was very similar to sort of like a non-multitasking system, because your system is literally doing one thing at a time. And so multi-level queue is a priority queue, and this is in a way very similar to round robin, but a little bit different in that, so you have your currently running task, and when it gets interrupted, you kind of have to make a decision. Do you keep running that task? Do you run a different task? And the way you make this decision is based on a priority queue, a priority system. So each task has priorities, and you sort of have to figure out which task has given the right amount of time given its priority, and then you kind of have this way where a task's priority is going to be a heuristic of how long it's run, with a bunch of different, related to a bunch of different things, like how long it's run, how long has it been since it's been run, what's its value over the priority. And this heuristic kind of comes up with a number, and whichever task has the highest number is the one that gets to go next. By the way, there is actually a C++ container called the priority queue in the standard library that you can use. And in that, you can define this heuristic. And so what happens is it's just a queue that's ordered based on this heuristic. So every single time you preempt a task, you update, you then look at your queue in the order of priority. So time has moved, so certain things may have gone up because their priority and the time since they've run has changed, and all of a sudden they have, now they have to be the ones that need to run. And also, so there's a lot of ways to kind of cut this, and in multi-levels you also have multiple different sort of queues of different natures, and this one gets run this often and this often, and so you can kind of imagine that you can see these schedulers get pretty sophisticated. But ultimately, with a priority queue in general, your goal is to make sure that the system that needs to be run now gets to do so, but while all systems get to be fed. So you're really avoiding this issue of starvation, where a queue of a particular task doesn't ever pop up to the top of the queue. And so you have to be very wary of that for these kinds of things, because say very high priority tasks keep on going into the queue, and a low priority thing just never gets to the top of the queue because of that. So these are some examples. And again, this really dives deeper into sort of operating system design and that, so it's a little bit out of scope, but wanted to kind of give you a bit of a perspective on all these different scheduling policies. And there are other ones too that I have not mentioned. Cool. So what about our processes? So our process is probably not just one big for loop or one big while loop. We probably want to do many different things, and we can do that sequentially, right, like in a game loop, or we can do that with systems that run in parallel to each other, or at least perceivably parallel in the sense of multitasking. And so the answer to multitasking within a process is the thread. And threads are essentially like processes, but they strictly belong to a running process. And one of the kind of key differences between a process and a thread is that a thread shares the same virtual memory and the same kind of memory layout as a process, meaning processes can't really communicate, can't share memory particularly easily. You can, but it's inter-process communication that's kind of a headache. But threads actually are able to communicate across that boundary very easily because they're in the same memory space. Inter-process communication is probably a subject I should add to this lecture, and so I might spin up another kind of separate thing because I don't think that's in this lecture, but we'll talk about that later. So anatomy of a thread, it's the same. The only difference is that, generally speaking, a thread points to its process ID. So actually, this thread is incorrect. The process ID, it should be thread ID. So a thread has its own ID, but it also points to the PCB, the process control block of its parent process. So when you close a process, you want all of its threads to close as well. But when you close a thread, it might not necessarily close your process. So how does context switching work, right? So the context switching is the act of an operating system taking one thread and switching to another, or switching between one process and another process. We talked a little bit about this with the interrupt service routine, and an interrupt will actually run and then determine which is the next task and then do so. But the main thing but this is actually done by the operating system. Now, the context switch is very similar actually to how a function context switch works. So when you switch functions, when you are in main and you call, whatever, printf, that actually changes your stack and all of those different things. But if you look at the code, you see that in the code, right? So when you compile your C++ or whatever, you'll actually see the stack changing and all of the registers being set and all of that stuff. So the main difference between that context switch and a process or thread context switch is that the latter is done by the operating system, not your code itself. And so, again, one of the main things, as I mentioned, between switching between processes and threads is when you're switching between the thread and another thread within the same process, you're not updating your virtual memory. But when you're switching between two different processes, you are. And that's because threads share that memory. And as I mentioned in a previous slide of this lecture already, the main impact of context switching comes from updating the state of the CPU registers. So when you're changing from one process to another process, you really have to ensure that the CPU is in the same state that it was in when you last interrupted that process. And also that you save the state of the process that you're interrupting, so that when you go and you restart it again in the future, you can start off from where you left off. And that's really critical, because if you don't do that, then the next time you run your process, something may be off, and then it may crash, or the output may be undefined. And so this is actually the most critical and core thing that an operating system does. And honestly, if you build a scheduler with a context switcher, like, you've built an operating system. That's essentially all it does. Everything else is just services and things to make running programs in that environment, as it's called, easier. So we already talked a little bit about deadlock, right? When you have a situation where you have, say, a non-cooperative scheduler, and one thing doesn't let go of the processor, and that's a deadlock, right? Everybody needs the resource, but you can't get through it. This also can happen in a preemptive scheduler if you're not careful, and this also can happen on the per processor per thread level. You can have a situation where multiple processes are trying to access a particular resource at the same time in a way that they can't. And same thing with threads. If you have a thread that's waiting on something that another thing's waiting on, that's another thing is waiting on, right? And that's a problem. Like, for example, if there's a resource that a task, only one task can access at a time, say like the audio card only has one way to access it, and another task can't make progress without having access to it, then we're in a deadlock. The way I always like to think about deadlocks is like a gridlock in traffic, right? Like, all these cars need to go in a particular way, but once you get into a particular state, no cars can move, and you're essentially stuck. Oh, I guess this is the same slide, just, I was like, yeah, where'd my image go? I guess it's right there. Cool. So this brings up this issue of what's called synchronization in concurrency. So not only do we need to have this ability to run multiple things at the same time, those things need to synchronize in some way. We can't just run willy-nilly and hope that everything kind of runs whenever it needs to, because if we do that, we'll get into scenarios where a system needs something and gets locked because a bunch of things are stuck in that bottleneck. And that's so we need to come up with a way to deal with that, and that's called synchronization. Another thing before we're going to go on, and I think an important thing to discuss before we discuss how do you accomplish synchronization, is what's called a race condition. So this is a key issue in multitasking where multiple tasks are trying to access the same memory at the same time. And because multitasking isn't actually atomic, right? When we're running stuff and pretending like it's at the same time, but it's not. Like one thing is happening before the other thing, and sometimes in a way that we may not be able to predict, right? And so there's a couple of different race conditions, and one of them doesn't matter. One of the race condition of read doesn't actually matter. If two tasks are trying to read the same memory at the same time, there's no real issue because the memory that's loaded from one and the other, if there is a state change on that in that from some other place, which is unlikely, it's okay because we've read it at the same time and we'll see the same memory. However, if one is trying to read and the other one is trying to write, or they're both trying to write at the same time, this can be a really big problem. This is exemplified by just a very, very simple situation where you have a shared variable between two threads and they're both just trying to add one to it. And that alone, like the output of that will not, you'd assume that if thread 1 and thread 2 are running atomically, then the value of I after they run will be the sum of times that thread 1 and thread 2 have been run in total, right? But if you run this without any kind of synchronization, that's not going to be the case. The actual value of I will be less than that value by some significant amount generally, because what happens is the load and the write at the instruction level may be interlaced. So thread 1 loads the value of I and it's the value 2, and thread 2 then loads the value of I and it's still 2 because thread 1 has not added 1 to that value. Now thread 1 adds 2 and then saves that to the register. Meanwhile, thread 2 does the exact same thing and it's also saving 2. So what happened is the value should have been 3, right? Because 1, like it started off as 1, it would have been 2 and then 3. But the output of these two running simultaneously ends up being 2 because the reads and the writes are being kind of overlaid on top of each other. And so this is kind of this issue where because the scheduler may be running on some things that we don't really know what's going on, there's a race condition of which piece of code runs when, even at the instruction level, and we have to be aware of that because what ends up happening is you have the situation where you may be operating on data that's being changed underneath you, and then as a result of that, you're writing to a place that has changed since that, during that time, you've been interrupted right at this the wrong moment, and you've loaded in data, and then another thread is now running and is doing something else with that data, and then changes that memory, and then you update that memory with your previous value, and then essentially you just undid the work that the other thread did, which may not be something that you want to happen. And so this is pretty common, and you'd be like, how often can that really happen? Well, trust me, like it happens all the time because computers run really fast. So even if it has like a 1 out of a million chance of happening, like it's going to happen like once a second. That's like the sort of different way of thinking when it comes to writing software. And so this is really important because now it really demonstrates that need, the synchronization need, right? If we have these two threads, we have to have a way to access this value I, and during that time ensure we're the only ones that can access that and lock everyone out, which yeah. So this kind of brings us to a couple of examples of synchronization problems, which I'll talk about, and these exemplify the need for different primitives that we'll then kind of discuss, and then we'll also talk about how to do them in C++. So this first problem is kind of the classic synchronization problem. This was presented by Dijkstra as a homework to his students, and now has become kind of like a standard, question and sort of thing that we all study, which is funny. But the basic idea is kind of a silly premise. You've got a table of 5 philosophers and 5 plates and 5 forks in front of them. And the goal here, so a philosopher can be eating or they can be thinking. If they're eating, they can't be thinking. If they're thinking, they can't be eating. And to eat, they have to be holding both a fork in the left and in the right hand. So they can't eat with two, like they're really hungry, so they need to eat, like crazy. They don't want to waste any effort. And the rules are kind of like if they want to eat, then they can pick up one fork, and then but they have to wait until the next fork is available, and then they can start eating. and then when they're done eating, they put both forks down. So if you just approach it that way, you just say, oh, that like, well, what happens? How bad can it be? But the problem is, if that's the case, you very quickly find yourself in a state of deadlock, or starvation, really. It's like kind of the joke that this is kind of the example of starvation in a system, because people like the philosophers are literally starving. But you can have a situation where a particular philosopher never is able to receive, to get in both hands a fork anymore. So if a philosopher is just picking up one, now you have a situation where a philosopher is holding one fork and is waiting for the next one, and that next one will never show up. And you can kind of imagine how this. Well, I'm not going to go through this problem too deeply. But just kind of an example of this. And so there's a very easy possibility, which will lead to deadlock, where nobody can eat even, because everybody's holding a fork. Or you also have the situation where you have resource starvation, where there is no deadlock because given philosopher does not get to eat. So a lot of different ways for the system to kind of evolve and turn into these different kind of bad things of starvation and deadlock. The solution is actually relatively simple. There's many solutions to this, but I'll talk about the one that Dijkstra brought up, which is philosophers only pick up a fork in a particular order, and say you're going, clockwise or counterclockwise. So if we all agree to only pick up a fork from the left on a left hand first, and then the right hand next, and that's the way that we deal with this, and that way. In that way, we can always ensure that a particular philosopher is not going to be deadlocked. The actual definition of this is a little bit more deep than that, where you basically label the forks from an incremental count of 0 to whatever, and a philosopher only picks up the one with the highest number that's closest to them first. And so it's not quite the left or the right, because you can kind of imagine where the number goes from 0 to 5, 0 to 4, you actually break that a little bit. But this algorithm will actually ensure that no philosopher will ever starve, and the system won't get into deadlock. There's another much more trivial solution to this, and this introduces us to our first kind of primitive, which is the mutex. And so if you can imagine a kind of butler that comes along and says, okay, hey, there's only 5 forks, but the butler owns the forks, and the butler goes up, and when a philosopher is hungry, they raise their hand, and the butler goes over and gives them 2, and when they're done, the butlers go and pick up the forks and go clean them off and stuff. And that will also ensure that our system never gets into a deadlock, because our butler is essentially keeping track of who needs forks and who doesn't. This may cause like starvation based on the behavior, but not given a sufficient amount of time. So a mutex would actually work quite well as well. This problem goes a lot deeper than this, and is sort of a big problem in regards to sort of concurrency in general. So if this is something that you're interested in, I do recommend diving a little bit deeper into it. And one of the homework problems will talk about one of these problems that's a little bit easier to do than this one. So with that, let's talk about mutexes, and or locks, as they're also known. And this is a very simple synchronization primitive that allows essentially a task to be given access to a particular resource while it's been locked. And this is actually done at a hardware level generally, because it's really hard to predict which task will get the lock if 2 tasks are running at the same time, figuratively. So as we talked about a race condition before, locks are usually done at the hardware level to avoid that race condition situation, because we want that mechanism to be atomic. So when we request the lock, we either get it or we don't, and there's no kind of question about it. So it's a pretty simple idea, and it works really simply as well. So in C++11, mutexes were introduced, and all you have to do is you lock the lock, right? And then if another thread tries to lock the lock, it's going to wait until that lock is available. And so in this scenario, as we talked about before, right, when we're operating on the shared variable A, we're guaranteed that either 1 or 2 will be accessing that at a given time. because if thread 1 gets the lock, thread now A is equal to 5, and it unlocks it. Thread 2 has been waiting, and now it gets to execute its code, and now A is going to be equal to 7. So you don't have that situation where A may be a number of different values based on what memory we read at what particular time. So locks, are pretty straightforward, and usually, by the way, the section between locks being locked and unlocked is what's called a critical section. And the critical section is essentially time where you're accessing a shared resource, and you want to ensure that only you are accessing that resource during that time, and no other threads are accessing it in that moment. So here's another example of a kind of a concurrency problem. This one's pretty classic, and it might not seem like a realistic problem, but until you kind of dig into it a little bit. So another problem that was introduced by Dijkstra, and this is sort of, you have one barber cutting hair in the barber shop. When a barber finishes cutting the hair of a customer, they go and check a room, which is a waiting room, and it's very important. It's a different room that has n chairs in it. If the waiting room is empty, they go back to their chair and they go to bed. They go to sleep. When a customer arrives, and obviously if there's a customer waiting, they would go and get up and then go to get their haircut. If the waiting room is if a customer arrives and the barber is asleep, they go and check on the state. Oh, actually, regardless, if the customer arrives, they go and check on the state of the barber. So they go into the waiting room, they go into the barber shop. If the barber is sleeping, the customer wakes them up and then goes back to the waiting room and takes a seat. If the barber is cutting hair, then the customer goes to the waiting room and takes a seat. If there are no more seats left, they just leave. They're out of there. When the barber wakes up, they go and they check the waiting room to see if there's another customer. So this may seem like a pretty straightforward thing. Like, how could this go wrong? Well, there's a couple of ways, right? There's a lot of nuance in these, right? How long does each one of these steps take? Well, one of the classic examples of this is, say the barber has a barber shop and the waiting room is down a hallway, right? But like the hallway is kind of weird. So like the barber shop is here, the room is here, and the hallway is kind of like this shape here, but the barber has a secret doorway, right? Like only the barber can go through this very quick way. So in this step of the customer coming, waking up the barber, and then going back to take a seat, there's a situation where the barber checks the waiting room before the customer has taken their seat, right? And in that scenario, they would be like, oh, nobody's here, I'm going to go back to bed. And now you've got the customer sitting in the room forever and waiting until another customer goes and wakes up the barber eventually. So this is, again, an example of sort of a critical section, meaning that checking the state of the room needs to be done in sort of a controlled manner, in a critical way, and every one of these steps and state changes has to be captured with some kind of synchronization, meaning when the customer, for example, goes and wakes up the barber it has to wait on the value of the waiting room to update. So somehow the barber needs to know when the customer has gone back into the room and taken a seat. And by the way, this is a system that can be described as a semaphore. That particular thing, the number of seats in that room, it can be described as a semaphore, and we'll talk a little bit about what a semaphore is in just a moment. But is a synchronization primitive to essentially count access to resources. But also you can kind of imagine how you'd solve this problem with a lock and a mutex that ensures that only one state change is done at a given moment. So if you can kind of try to define the system as a sort of state machine, right, you only want to change the state at one given time, because as you can see here, only one behavior is taking place at a given time, and you can kind of ensure that all those different states take the same amount of time to change, or are blocked by each other, so only one state change can occur. So let's talk about semaphores. Semaphores are essentially a counter. They're just a variable. So you can kind of imagine a semaphore that you can count down to, like, count with a particular number of values, or you can also treat this as a binary semaphore, which is really just a counting semaphore, but with just one value, which is, it goes 0 to 1. And semaphores come actually from this, flag signal semaphores, which are used in ships to communicate across long distances, and it's kind of like a type of Morse code almost, but with using flags, which is pretty cool. But they're very unsimilar in like how they actually function, but that's where they get their name. And semaphores define two different behaviors. One is weight. So the weight will decrement the value by 1. If the new value of the variable is less than 0, is negative, then the task that calls P has to wait and is blocked. So it gets added to a queue, generally a FIFO, and it's waiting. It's essentially stuck, right, and waiting. And a signal will increment the value of the variable by 1, and then it will check, like it'll keep running this task. It's essentially like saying, hey, I'm done using what I'm using, and then the semaphore will take a look at its queue and then run the next task that's available on the queue if the value has gone up above 0. So you can imagine you can go pretty negative. Say you have a binary semaphore and you have 5 different tasks trying to access it. Well, you're eventually going to go into the -4 because they're all asking for it, right? And so this is you can be in a situation where you have to wait for a very long time, or something else actually has to signal the semaphore for those other 3, because you can imagine in that scenario, right? One will, if 4 different tasks are waiting on a semaphore that's only a binary, one will get it, and the other 3 are in the negative, so the value is now -3. And then when the one task that got it finishes and then signals the semaphore, then the value is still -2, and it's only going to, it's not going to actually well, actually that's not true. It's going to launch the next one because, sorry, the signal, if the value is negative before the signal, it will transfer a new block. So as long as it's negative, it will let the next one waiting go. So you can kind of imagine an example of this is changing rooms at a clothing store. So say a changing room, a clothing store only has one changing room, and you have a queue of people that are waiting, right? They all show up at the same time, or at a similar time, right? One will get in, they'll be the first person that gets it. The 3 are kind of queuing. When one leaves, right, it's like signaling the semaphore, another one will go in, and so on. If you have 4 changing rooms, that's like a semaphore of 4, right? So if 10 people show up, then the first 4 people get to the changing rooms, and as they pop out, they will then signal different ones to go in. And so that's the kind of general idea here. And you can also kind of apply this semaphore idea to that changing room. To the sitting room, the waiting room for the sleeping barber's problem, because now you really want to make sure that you're signaling and waiting correctly, right? So for example, when that operation of the customer walking back to the waiting room is essentially a wait, and the operation of the barber on that is then a signal. Or, sorry, the other way around. But yeah, you got my idea. Cool. So another example is a more kind of abstract example, is just the producer-consumer. So like, in this case, you have one task that's outputting to a shared memory buffer, and another task that's receiving that from the shared memory. And so you just have to synchronize these two. And this is done very clearly and easily with a mutex, with a lock. So the producer is outputting to this shared memory, again, in this critical section, and then the consumer is reading also in a critical section. And so that ensures that the consumer sees the current version of the memory, because if you just let this run, there's a very high likelihood that the consumer will read the shared memory buffer while it's in an inconsistent state. So the producer is currently writing to it, because that takes a certain amount of time. It's not going to happen all at once. And so the consumer may read from the shared memory buffer when that data is an inconsistent or only half read situation. If you ever downloaded a file that failed in the middle, you can kind of appreciate, the outcome of this, where maybe you're downloading something and it doesn't all download, and then you're trying to read it and it's not going to work. So this is a very classic, very simple one to solve, because you can solve it with just a basic mutex with a critical section. So similar to this idea is the sort of readers-writers problem. So in this case, you don't have basically two tasks, one reading, one writing. You have many tasks that may be reading and may be writing at any given time. And so there's three different sort of problems as defined here. And one is the reader's preference. And the reader's preference is essentially, if the shared is only open for reading, no read will be kept waiting. Meaning, because we talked about this before, right? Reading a shared memory location is not the race condition that we're worried about. So if a bunch of readers are trying to read all the time, then let them go, right? Don't ever block a reader. This is what's called a reader's preference. But this has a downside, because if we have a writer may be starved out, because if readers are constantly coming in and preempting and being prioritized over a writer, there's a chance that the writer will never actually get a chance to write. So there's an alternative, which is writer's preference. And in this case, it's a bit of a subtle difference in that a writer will not have to wait longer than possible. So when a writer asks for access, all the readers that are currently in the queue will complete, but other readers will wait until the writer is done, and then the other readers are allowed to kind of continue. And so writer's preference basically ensures that a writer doesn't have to wait forever. Eventually the readers will be done, and then it will go. And then there's a third option here, which is what's called the bound time, where no task is essentially allowed to starve. And so obtaining a lock or obtaining access to the memory should only take a bound amount of time. And this one, is actually pretty effective, but also means that we may have to interrupt a writer or interrupt a reader, and so our system has to be a little bit smarter of how to deal with those scenarios. Cool, so let's talk a little bit about kind of how you accomplish a lot of this stuff with C++, and this will be pretty quick. So this is how you do it. Threads are actually really simple. In C++ 11, threads were introduced, so you don't necessarily need to go at the operating system level to kick up threads. Although I will argue that it's the standard library thread system is limited because it doesn't support all the different capabilities of every single platform, because like Windows and Linux deal with threads differently, and you can't put something in a standard library that doesn't work on both platforms. And so sometimes it does make sense to go down to the native thread implementation. And actually, the C++ 11 thread library does provide that capability to you through native thread, which will give you a handle to the native thread pointer on your particular system. So then you can plug that into, say, the Windows threading capabilities and so on. Because the underlying implementation of this threading system it has to be at the operating system level. But as you can see here, right, like you basically can create a vector of threads and push back threads, and you're passing back this value which is the hello function, which is calling it, getting the thread ID. It's just like calling this thread get ID. It's very simple. And then there's this function called join, and join will basically try to end the thread, or in theory, technically, it joins that thread into our process or into this current thread. But join doesn't kill the process. There's no way to kill it directly. You're basically waiting until they're all done. And so join will just wait, will block until hello is joinable. And so there's also a function in the threading library called joinable, so you can check if a thread is joinable before you try to join it, because otherwise you'll get stuck forever. And if you say like you have a for loop, like you have a thread that's running like an event loop or something, the way to deal with this is you have to have a shared piece of memory that tells it to quit or something, and that way you can set that flag, see if it's joinable, and then join it, and that's the clean way to clean up your thread. But yeah, this is pretty straightforward, and please feel free to check out this link that will talk about this a little bit more depth. Another thing that you probably should think about is yield. This can be used to yield the current thread and let other threads run. This is actually a pretty common thing if you're just running and you have many, many threads and you want to make sure that everybody gets a chance, because a thread may lock the process. And so a yield will let other threads essentially do work, which is pretty valuable. Also on the left here, the code I've changed a little bit to kind of demonstrate threads can be used with lambdas as well, which is a very nifty new feature in C++. And so in this case, I'm just wrapping the hello call in a lambda. You can also create threads on function pointers like standard library function. Very easy to kind of use this capability. So also, C++ now supports locks and mutexes since 11. Very straightforward. You create a mutex and then you lock and unlock it. You can also use what's called a lock guard or the unique lock to capture the mutex. This is mostly a convenience thing. It just is it's a wrapper around the lock, and so when you create it, it captures the lock or waits for capture, and then when the function goes out of scope or this particular variable goes out of scope, then it will release the lock as well. So it's just kind of a nicer way, because you can see above I have to call mutex.lock and then mutex.unlock, but what if I forget, right? And so the unique lock and the lock guard kind of codify this in a very consistent way, and using the destructor of these objects ensure that we unlock the lock that we captured in the beginning. The only real difference between unique lock and lock guard is that lock guard only supports the locked state. So when you use a lock guard and you capture a lock, you can't unlock it, you can't manipulate it. Whereas with a unique lock, it supports both the unlocked and locked states. So you can manipulate the lock still. But still it'll behave correctly when you leave that section, and it goes out of scope and all that stuff. So they're very subtle. They're kind of similar, and they're also kind of superfluous if you don't want to use them, but they are sort of like best practice or whatever. Another thing that's really, really valuable, so sometimes you want to only unlock in a given scenario, right, with a conditional. And so in this case, you can use what's called conditional variables. And here what you do is you pass to a conditional and you're waiting, and you pass to it some function that returns a value of bool, of false or true. And when you do that, you actually have to call notify on this from a different thread. So thread 1 is going to wait and will only unlock given a conditional statement. And so you can kind of imagine like a prime number generator or something, where you have thread 2, which is notifying for each value that's being updated. And so now the value, okay, hey, 1, 2, 3, 4, right? And so now we notify a thread, hey, it's safe to read this value. And then thread 1 is going to check and is only going to do work given a particular value is a particular condition or something like that. So yeah, it's there's also a couple of other versions of this, such as wait for and wait until, which will wait for a certain amount of time before they unlock, and this avoids a deadlock because, as you can kind of see, waiting on a conditional, say we only call notify all one time, we may be waiting forever, which is a problem. And the way that we make this work is we actually have to operate on a mutex, by the way. So a conditional variable is built on top of a mutex, just like the lock guard and the unique lock we saw in the previous slide. This one is a little bit out of scope for this lecture, but something I wanted to bring up and get on everybody's horizon, right, is future and promises. It's kind of an underutilized feature of C++, but it's been introduced at the same time as all these other synchronization things. And what's really cool about this is you can have a future. It allows you to sort of promise a result from one thread to another, or from one function that runs on a thread to another function. So you can essentially create a future, and you then you create a promise that then another function will return. And as you can kind of see here, right, this is just code from the C++ reference documents. But you can essentially then call a thread that will then return, you can pass to it a future, And then when you call promise set value, what that does is it's going to set the value at some time, and then in this print int, it's going to get the future. And so it's basically just like a bunch of conditional variables and mutexes and locks and stuff. It just allows us to set a value that a function that is then utilized somewhere else in our code in a synchronized manner. And so this int x equals future.get is going to block until prom.setValue10 is called, which is kind of like a really nice thing. In this very trivial example, it's not very cool, but imagine doing this for like an HTTP request, which may return at some point, but you want to keep running code. So we're like, okay, I'm going to request a URL, and when we get it, but at a certain, like I want to run all this other code, and then when I have it, I only want to keep going past this particular location in code once that data has come in. So it kind of saves you a lot of complexity in multitasking with especially things that take a long time. So one super experimental thing that in C++, but this is a very, you can implement this with a bunch of semaphores, which again, C++ doesn't support semaphores directly, but you can implement them with, a lock and a variable. But a latch and barrier are really valuable things. They're introduced in like Vulkan and stuff, so it's valuable to think about. But in a way, a latch is essentially like a counter. It's almost like a semaphore that we only want to keep going for any one of them when everybody has been notified. Everybody's hit this point in the code. So a latch will be set to some value, and as tasks hit the latch, that value will go down. And when the task hits 0, then all the tasks can keep running. Now, and the barrier basically does the same thing, but the only difference between a barrier and a latch is that a barrier can be reset, and a latch cannot. So it's sort of the classic definition of a latch just goes one way. But a barrier is essentially like everybody gets up to the barrier, cool, let's go, next barrier. And actually you can think about this as very much as a valuable thing for games and game development, because sometimes you want to have a bunch of different AIs doing different things, and you only want to move on to the next frame once they've all completed the work that they're doing. Another example of this is actually the algorithm deterministic lockstep, and this is a networking algorithm to ensure people can't cheat. So that in deterministic lockstep, every client that you're serving, so this is a networking algorithm, every client that you're serving tells the server what their next action is going to be, and then the server waits for all of the clients to tell them the action before updating state to all of them and then waiting for the next action. So this is a very classic example of a barrier. And the reason we do that for deterministic lockstep is to avoid cheating, right? Because say I have a fast internet connection and you don't, I can maybe spam the network with a lot more activity, and I can do more things in that same amount of time than you can. And so this way, deterministic lockstep kind of blocks and ensures that each client can only do a certain amount of things during that amount of time. Cool. I'm actually going to pause. I'm going to split up this into 2 different lectures because this has gotten quite long. Yeah, I'm just going to stop here, and then I'll continue in just a moment.